Welcome in everybody. My name is Soroush. I'm the tech lead here in AI Club. Today is day two of AIX data training. We're going to talk about supervised machine learning, supervised learning. Can everybody hear me okay?
Yes, you sound amazing.
Yes, all good. Awesome, awesome. Alrighty. Without further ado, let's jump into it. Okay, so um we're going to do firstly a extension of what Sean went over with you guys yesterday with the data set at the EDA workshop last night. So we're going to explore a few different ways um, for supervised learning today together. One of which is going to be regression, which helps us predict numbers for math scores. For example, some stuff like, um, let's say, a writing score, or depending on your use case, let's say weather. And we're also going to talk about classification, which can help us classify different categories. For example, if you have 10 different flowers, what you could do is use classification to say, for example, oh, is this a rose? Is this I don't know. I'm not really good with flowers or orchid or whatever the case might be. But just to keep in mind, we're not going to go over vision today. We're not going to do anything image related. But it is a good thing to keep in mind that also a lot of vision models do use classification. So we are going to let's start. Let's start by importing some of the necessary packages in the data set itself. So first thing I'm going to do is, of course, import pandas as PD. And I'm also going to just set an option. Max columns to 200 so we can see everything all together. Then I'm going to import, so Scikit-Learn, the model selection, import, train, test, split. So we can split our data accordingly for our train. Also, since my data set is on Kaggle, I'm going to import Kaggle Hub, and I'm going to give it the path for my data set. So path is going to be Kaggle Hub, data set dot download. Here. There we go. Now let's print path the data set. And also we're gonna convert it into a data frame. PD dot read CSV, and we are gonna give it our data set. Yes, that. Okay. Any questions so far for what we've done? Not much. It's just importing the data, making sure we have the data set. No, no. All right, we will continue then. Okay, so this is a pretty interesting data set. Because if it runs, I can show you guys. I'm gonna wait for it to run the first block, but till that does, it has a few columns that might be quite might come in quite handy. So, for example, it has three different test scores. It will have, whoa, error already. I may have displayed dot max. Okay, my fault, guys. Okay, so gotta go behind the data set. There we go. Okay, so this guy has a few interesting factors to it. So we have gender, ethnic group, parent education, lunch type, test prep, parent marital status, practice sport is first child, no sibling, number of siblings, transport means, uh, weekly study hours, math score, reading score, and writing score. And you can see it only printed a few of these, but it is a wide range. So we have 71s, we have 80s, we have 90s, we have fails. So it is a very, very versed data set. Now, the reason we're using this is because there is a lot of columns that we can take in as input. There's a lot of factors that we can take in as what you call labels, and are we can experiment with different scores as the output. So we can predict, for example, the reading score by giving all of the others as labels or input columns. We can do math score or writing score. So with that out of the way, since we have that already, let's start with regression. So what is regression exactly? So regression finds relationships between inputs. And for example, if you have if there's a student who does do test prep and has 10 points higher on average, regression tries to capture that as a trend. And our target is, for example, here to have a math score between 0 and 100, predict a math score between 0 and 100, to see that one particular student who is taking prep course, what's the difference? Like, what difference does it make for a student who is taking those test preps or has a better environment, growing environment, to other ones? For the sake of this meeting, we're going to go over linear regression, and I want to explain briefly what linear regression is. So with linear regression, we will assume that all of the relationships are linear. Um, this might come in initially as, oh, but not everybody is the same, or not everything is the same. You are correct. That is absolutely right. But a lot of these trends tend to fall on similar, let's say, lines. We will see later on how that actually works. This is actually, from what I know, this is collected data and is not generated data. So we have a good shot at seeing a real graph at the end of this. But how does it work? So it draws a line through the data that minimizes the errors between the line and the actual data that we are inputting into it. It's like finding a ruler when you try to measure between like two screws or two screws on the wall. You're trying to draw a straight line between the two. Now imagine there's like a cluster, like there's a bunch of screws. You're trying to find like the very, very middle, what line crosses all of them, or is a good mean of that. Um, but then with that, there comes some limits. As we mentioned before, not every pattern is linear. And that is something to consider. But also, I am going to later on mention some stuff not related to nonlinear regressions. You can also do regression with polynomial functions as well. So our plan is to take in some of these, for example, the gender, the ethnic group, parent education, and see what would be the prediction for their test scores. So let's just do that. First thing we'll do is from Scikit-Learn, the linear model, import a linear regression. And then from Scikit-Learn dot metrics, import mean absolute error, mean squared error, and R error. Now I will explain all of these, do not worry. They're like, what the heck is this guy importing? Let me cook. I got you guys. So let's take in the features. So what we talked about is what? Let's say, do you guys have an idea of what you want to put in? Do you guys want to do all of them? Do you want to do some of them? Feel free to put it in the chat or open your mic. Which ones do you want to
All of
see?
them.
All of them? All right, let's go all of them. Okay, so let's start by gender. What's next? Ethnic group. Um,
To help you out here a little bit, if you do the code cell under it and do df.columns, you can just paste from there. Like
like this?
yeah, I think that should work. Oh wait, no, you don't even put that part. Oh, you're missing a parenthesis right there.
Oh, there we go.
There you go.
Yay. Okay, so thank you, Sean. All right, gender, I think. Okay, so I'm gonna get these. Bada bing, bada boom. All right, I'm gonna put them in one line because why not? Long lines save more space. Look ugly, but actually I'm gonna do it in two lines so you can see all of them. Never mind. Okay, so now what? Let's see. Let's put them in function terms. So I'm gonna say x equals df in features. And our Y, which is going to be our result at the end, is going to be our data frame. Which one do you guys want to do? Math, writing, or reading scores? Math. All right. Let's do math score. All right. Now we're going to do x dot x encoded to equal pd dot get dummies x. And we're also going to split the data. I'll explain what the dummies is in just a second. Let's see. Train x underscore test x underscore wait. Y underscore. Train Y underscore test to equal train test split x encoded y as our output. Our test size is going to be 0.2 and a random state of, let's say, 42. Okay, so what are these? I'll start down here first. So X train, X test, Y train, Y test. Why do we have two of each? Why do we have the test size equals 0.2? So that means if I have, for example, let's say 1 million data points, 1 million rows in my CSV file, I am going to split that into being 20% only and only for testing, and then the rest to be for training. So with that being said, the random state just randomizes the different well, it randomizes the test rows that it will get, and that is that. Any questions? Right, no questions. Awesome. Okay, so I just realized I forgot to explain get dummies. So get dummies is a function in pandas that will help us convert as many zeros and 0, 1 values, or yeah, 0, 1 values into different ones. So for example, if we have a data frame in our case, the name of the original value or variable is going to be more readable afterwards for our computer. Instance of that being, for example, if you have a list that says 0, 1, 2, 3, you can change the columns to be named A, B, and C, depending on how you would like to frame that. So let's see. Now, already, we're going to create our model. So model is going to be a linear regression object. And what we do with this guy is we will fit our data into this. So model dot fit. We will give it X. Actually, I'm going to ask you guys, do you think we should give it X train or X test? Anybody?
My answer?
You can answer.
Uh, I'm gonna say X test.
X test. Why do you think is X test?
I don't know. Wait, I don't know what the difference is between X train and X test.
That is great. That leaves us room to explain. Awesome. So, uh, Matthew Mar, I don't want to pronounce your name wrong. I apologize if I did. Oh, okay, awesome. You are correct. It is X train. The reason for that is the testing portion is mostly for the validation of the model. It is for us to go over that 80% and then be like, oh, now let's see if it actually can predict. So the test is a smaller portion of our data set, and the thing we have to fit into the model is the training data, not the testing data. So thank you guys. Thank you all for participating. So this is going to be X train, and we also will give it Y train. Awesome, awesome. Now, there is before I tell you guys about this, I want to make something very clear. So, main difference between supervised learning and unsupervised learning is that in supervised, we will give our model both the input and the output. We say, okay, this is all I got. This is all of my data set, right? I want you to predict some stuff for me. In a unsupervised learning state, what you will do is you will only give the inputs to your model and ask it to figure it out. Now, there are many different levels, many different ways to do this. But for the sake of this meeting alone, um, we're going to go over supervised. Of course, it's a title. So we are going to give it both the input and the output. And then once we want to get some predictions, what we're going to do is we're going to give that 20% that we separated for testing. Now, after we do that, how can we evaluate if our model's accurate? Remember, we have a Y test as well. That is the actual output that we have for X test. So we will have our model predict, and after it does, we'll just compare it to these ones. We can also get the cost correct. So since I have imported these three already, we'll do those first. So let's do the MAE, or mean absolute error, to equal, who would have guessed, mean absolute error. And we will give it Y test and Y pred. Then we have MSE, which is mean squared error, which will be, again, mean squared error. Same ideas, same execution. Y pred. I'm going to just say R square R2 equals R2 error. And in here, I will fit in Y test and Y secret. As a matter of fact, I think R2 is score and not error. Let me double check that. R score. Yes, it is R score. Oh, so it is R score. That is my apologies. Okay, awesome. Now, done. Easy. So I'm gonna say, format it nicely. MAE is MAE. MSE and R2. All right. So let's see. Error already. Huh.
It's because the X that you put in there wasn't capitalized.
Oh, as I'm getting old. Thank you, Sean. X encoded is not defined. This one is capitalized though, which is weird. There we go. That should do it. That should do it. That will not do it. Let me check this. Let's see. All right, there we go. Okay, so I had some typo somewhere. All right, so average error is 4.76. This is in score points. MSE square error is 35.86. That is not that great. And then how well the model fits from 0 to 1, we're getting a 0.84, which is 84%. And that's not that bad. It's not great, but it's not that bad either. I'm gonna hover over this for a few seconds. Do you guys have any questions about this? All right, no. So let's explain them a little bit more in detail, right? So MAE is the average difference between our predicted and actual math score, right? If MAE is 10, our predictions are off by 10 points on average. Uh, uh, the lower it is, it would be, of course, better. Now, when it comes to MSE, these are more toward the more bigger mistakes per se. So it is useful for comparing models, but it is a little bit harder to directly interpret them due to it being a square point. It literally squares our mean error. And then when it comes to R squared, this will tell us how much variation in math scores our model explains. So zero is a no fit, one is a perfect fit. A R squared of 0.3 means 30% of the scores are captured by our features, like gender or test prep. For this data set, we didn't expect that much, but we got a pretty decent square out of this. And it is important to realize why this is important. When you train a model on the Datathon, when you're doing it on your own for a separate project, for whatever the case might be, it is important to keep track of these errors, these accuracies on the time, right? You don't want to leave it for the end. You don't want to train a model. You don't want to spend thousands of minutes, thousands of seconds, hours uh, trying to see, oh, what's going on here? Oh, this thing's going to train. It's not. Is it going to be good? Is not going to be good? What you usually do is you will give it a portion of your data set to minimize the training time and then use these errors or average points to determine if you're on the right path or you have to change some stuff, if that makes sense. Any questions so far? Alrighty, moving on. So let's go over classification so then later we can compare the two. Um, what if we want to compare not only not that their test score or their math test score, what if we want to do if they're pass or they will fail? Uh, that's going to be different. That's going to be completely different. Uh, because with the regression model, you are not able to generate anything that is text. So cannot do that. Well, what you could do is use a classification model to do that. So for this setup, we're gonna use something called logistic regression. Pause. We just said we're not gonna use regression. What the heck, Rich? Why are you lying to us all of a sudden? Actually, I am not. So, logistic regression will predict the probability of a category, then pick the most likely one. So this works it works in a way that classification does, and that's why it is considered a classification training method and not a regression. So the way we're going to go for this is we're going to make a pass or fail column. For scores above 60, we're going to say put a 1 or put a pass, and then for less than 60, we're going to put a 0 or a fail. Instead of MAER squared, we're going to use accuracy this time, uh, which is pretty much how many correct answers do you get compared, how many correct predictions do you get compared to the actual data. So to get started with that, we are import from Scikit-Learn dot oh, matrix. Okay. So I will explain as we go for what we imported. Though just know that accuracy score and confusion matrix are two metrics that rhymed. Confusion matrix and accuracy score are two metrics that we are going to use to determine the accuracy of our model. So let's say Y class equals, we are gonna change this, correct? So we're gonna say DF math score bigger or equal to 60. I would say that is a pass as type int. So then, as I mentioned before, this is going to convert our math score column into being a 0 and 1, fail or pass. So we're going to do a X train, X test, the same idea. Y train, Y test equals. Actually, I'm going to add a C here so it doesn't get confused with the other ones here for classification. And we'll do train split test. X encoded. We're keeping that. Did I do lowercase here? I did do lowercase. Okay. X encoded, and we do Y class. We'll do test size of 0.2 again. And a random state of 42. Okay. So now, after we get all of those out, we split our data. Let's train a model. Let's say CLF equal logistic regression. And in here, we're going to give it a max iteration of 1,000 for now. And I'll explain why we're raising this in a little bit, but same idea. CLF.fit, and what do we fit in here? X train and Y train as we did with the other one. Y pred C equal, let's predict. CLF dot predict, and we will put in X test C. Okay, so everything looks pretty similar, right? Besides the class names, logistic regression, the linear regression, everything else kind of looks the same. We haven't changed much. And as a matter of fact, when it comes to the accuracy, it is also the same thing. So I'll do a accuracy score. Again, same thing. It will just make an object, Y test C and Y prediction C. And the matrix is going to be confusion matrix to equal, Y test C and Y spread C. Okay, now let's print the results. See if this will run. Yay, okay. I mean, I guess since we're not running all of them together, we wouldn't need to. I'm just gonna put this here. Oh, it's test split. There we go. Here we go. So if here we go. All right. So if I come down here, let's see if we will run. I have again same problem. There we go. Okay, awesome. So we have a accuracy of 0.88. So how much is that? 88%, 88.2%. So I want to ask you this. How different is that from this one? About 4%. What's going on here? Why do we have more? Why do we have less? So depending on what data set you're using, you would have to alter the model that you're going to use. Um, is it worth investing time into like doing 10 different models just to get the absolute best out of it? No. There are many research papers about this that compare different types of learning to see, oh, why is this one better? Why is that one better? But the truth of the fact is, it really depends on your use case. If you are doing a classification of, or let's say if you are doing, if your data set works with more math calculations, you would have to use a linear regression model in our case, like between these two. But if you would have to do something that is just giving back a value of this class or that class, or it's this category or that category, you will use a classification. Each of them have their pros and cons, but here we see that when you limit your data into only being a pass or a fail, the accuracy goes up. Do you guys have any questions so far? I'm going to demonstrate the confusion matrix as well in a second. If I can draw a graph for it, it will be very nice. Alrighty, no questions. Awesome. So let me see. All right, so I'm going to, for our, make another one actually. Make another code here. I'm going to import matplotlib dot pyplot as PLT. And then, do we need anything else? Do we need any? No, I don't think we need anything else. I think we should do that. All right, so that should do. So we'll do PLT dot figure, and let's make a figure of size 6 by 4. PLT dot bar. Am I doing this right? That'll be for the accuracy. Yes, let's do the accuracy first. Let's do PLT dot bar, and we'll give it a accuracy like so. Accuracy, which is our evaluated score up here. And we will, let's just give it a color. Like, is everybody fine with sky blue? Anybody wants a different color? Sounds good. All right. PLT dot y limit to be 0, 1, and PLT dot title also. Let's say classification accuracy. And a font size of 14. PLT.y label. Accuracy between, and we'll do 0 to 1. Instead of doing a percentage font size. 12, a little smaller, and PLT.show. Let's see if this runs first. Have made a mistake here. There we go. Okay, so this is a very, very simple representation. It's a bar chart that shows our classification accuracy to be 80 something percent, right? Now, if I want to make another one for our best buddy confusion matrix, which was the initial goal, PLT dot figure again. This one I'll give it a fixed size of 6 and 5. And I think we will need something. Seaborn as SMS. Okay, awesome. So now we can create a heat map of where everything is closest. So SNS equals, well, SNS dot heat map confusion matrix as the main parameter, annotation to be true, FMT CMap stands for color map, in case anybody's wondering. Blues. X tick labels and Y tick labels. Predicted fail, predicted pass. Actual fail, and actual pass. Okay, just put this on 2 lines so it's more visible. There we go. All right, so PLT, I'm going to copy these, so save time. Title is going to be all right. Let's see how many. Okay, there we go. So, what do you guys see there? We have 4 squares. So, um, if we had more points, it would be a better representation, but I'm gonna do my best. So here is how this guy works. A confusion matrix says that our model predicted 3,883 of the inputs to be a pass, and these are what actually passed. So it was an actual pass and it was a predicted pass, but it was 329 of them were predicted a fail, but were actual passes. So this is our loss. This is what we're losing in the training process. This is the false prediction that will cause our accuracy to come lower. And then this is our predicted fail and actual fail. So it means our model predicted it's going to be a fail, and it actually was. And this is the opposite. So it was a predicted pass, but it was actual fail. Um, I hope this helps. Is there any questions about this? That is a-okay. Awesome. All right. Let's see. So now we have these 2 graphs, but let's actually compare the two. Let's see what would be a good way for you guys to measure these. So yes, we saw a accuracy score, and we also saw our, where'd it go? We saw actual score, and we also saw a how much it fits into the model for our linear regression model. And the difference was around 4%. That is not bad. That is actually a pretty close call. But, oh, I had that. Okay, so in this one, all right, so let's see. Thing is, now if we go over the exact same charts that we see, there's not much that you can take from this because we only compared one of the models. Well, we can put our regression model on the same chart and then see the difference close to each other. That is how you would represent it in a real world setting when you have a very, very large data set. My suggestion for you guys is when you go work with or for this datathon per se, when you work with the data sets that are given to you, it is best to split the data initially, make sure everything runs well, compare. Good thing about drawing charts is that you can store them and visually compare them, right? So that before you train your final model, you have a wide variety of categories or wide variety of configurations to choose from. Um, Another point is in the real world, in workspace, for example, if your professors ask for something, if you go to work in machine learning, if that's what you like to do, what happens is you would have to show some data to people. It's not everybody's technical. A lot of your managers are not going to be technical. So it is nice to have data representations as charts. Okay, awesome. Any questions, guys? No? Okay. So there is a few honorable mentions that I would also like to go over. Um, Decision trees. You may have seen these happen before. Actually, if I pull up a decision tree uh, over here, we can see age young senior. Is it middle aged? Yes, we stop here. So let's say this is looking for what? Is not necessarily looking for anything. Okay, this is a good one. This is a good one. So this is an interest rate quote. If you have an excellent credit score, then it will ask you if the car that you're buying is more than 10% of your income, then you will have if that's the case, you'll have higher car payments. Rates are going to be 5 to 6.5%. If it's less than 10%, it's going to be lower payments, so 4 to 5.5 interest, right? Now, I believe this chart is old because right now I don't think you can get anything less than, because it says, for example, for below 600, you're going to get 6 to 7.5%. Good luck. If you find it, I'll buy cars from them. So point is, I want to ask, do you guys think a decision tree like this would be a good fit for our data set? Can we do such a thing?
Um, I think uh, what would be in this example, what would be like the acceptance rates for our data set? Would that be the test scores?
Acceptance rate, it would be the test scores, correct.
Then
So you
yeah.
can say the math score.
Yeah, I think it might be a good fit because maybe there's going to be branches for like if they play a sport versus if they don't, and then a higher score depending maybe. I'm not
Mhm.
sure. Yeah.
Now you are correct, but there are that's a very good observation. You are right. It can be used for our data set. However, there are some cons to it. Um, it can get too detailed. If you have too many columns, it will get too detailed. It's gonna be like it's gonna constantly look for the perfect fitting option. And that's not always the case, right? We talked about the accuracy in linear regression being a little bit edgy because, oh, it's a linear line between all of them. How's that gonna work out for a decision tree? And another con of it is greedy. It makes greedy decisions. So on let's say on the tr split that we do for training and train test split that we do, it most likely will not give the best result, which will make it a little tougher to work with because then you have to start actually working on it and making sure it play with the numbers, make sure everything is going to work properly. Now, uh, another one of these that I have over here is random forests. So random forest is quite similar because it combines many trees. It uses the same similar structure with the trees, but it combines many more trees, and it does get a better accuracy overall because of that. Um, and another honorable mention for this is going to be support vector machines, where we are going to find the boundaries between categories or fit lines for regression. So if I would draw something about I would actually like to demonstrate this a little bit more. Uh, so on a for you in a SVM model, what you would do is let's say you have a graph going like this. With this graph, let's say similar to linear regression, have a line going across, and your data is split all over. You have data split all over. The way SVM works is you're gonna draw what we call support vectors. Actually, that is horrible drawing. I apologize for the eyesore you're seeing, guys. These two lines are gonna be parallel to each other and to our main line over here. So if you want to know what they are called, the middle one is what we call a decision boundary, which separates uh, into two categories, technically. And we have a margin between the two supports that we have over here, this one and this one, which means it's gonna, wait a second, why is my laptop? Excuse me. Excuse me. Okay. So those lines, the supports will give us a boundary between the decision and the actual data that it is good to study them if you like to. I will put some links down here after we are done with this meeting, and then once we publish the workshop Zoom recording in YouTube, I'll make sure you guys have the notebook as well, or the links. Is that possible, Sean? Can we give them the notebooks or no? Are we giving
Yeah.
them the notebooks?
Yeah. We
Yeah.
can.
Okay, awesome. So that's that. Those are all the basics. Those are all you need to get started with supervised learning. I forgot the name for a second. I was like, whoa, what's going on here? Um, that's pretty much the start. That's pretty much what you guys will need to have a decent understanding on the Datathon. If you want to go that route, I do suggest, of course, studying more. It's not going to be enough, but it is a prep meeting, so happy to be here. Do you guys have any questions? Anybody? Hit me in the chat. Hit me in the chat. Seems like everybody is okay. All right. That will be all the topics I have for tonight. Hopefully you guys enjoyed and there was some stuff for you guys to learn. Um, Feel free to reach out in Discord if you have any questions about the notebook later on, or you have any questions about Datathon in general. Put it inside of the either general chat or Datathon Q&A, and we will be more than happy to answer you guys. Uh, Alrighty, awesome. Everybody take care. Have a wonderful evening. We're going to be back with you guys tomorrow for unsupervised learning. That is going to be a very, very interesting topic. I do suggest you guys stopping by, and I will see all of you guys on Thursday.